And so here's a nice application to the angular and linear speed idea. So I've got a satellite here that's in orbit 1,000 miles above the Earth's surface. If it takes 4 hours to make an orbit, what is the linear speed of the satellite? Okay, so there's an extra side note, something that's needed here is that the radius of the Earth is approximately 4,000 miles. And so we've got to look at this as a circle. Now the Earth itself is slightly off from a circle. It's more of an ellipsoid, slightly swollen at the equator. But we're going to use an approximate 4,000 mile radius and think of it as a sphere. Cross-sectionally, then it's a circle when you take the orbit into account. So we look at it, maybe I'll draw it over here, as a circle. That's not so good of a circle. I'm going to redo that one. So you can look at it as a circle where the orbit is, actually it's really two circles. You've got the inner circle is the Earth, the outer circle is the orbit. The inner circle has a radius of 4,000 miles. And then the distance between the two circles, the surface of the Earth and the orbit, is 1,000 miles. Okay, so between those, that's 1,000 miles. And so the total radius of the orbit from the center of the Earth is going to be 5,000 miles, right? So the final radius there is then 5,000. So we're looking for the linear speed. Well, linear speed is calculated two different ways. We don't know the arc length, so we're going to have to work with the r omega, right? So v equals r omega. Now I don't actually know omega either, but I know theta and t. I can get that from the problem. So actually, let's look at that first. Omega equals theta over t. Well, the second sentence says it takes 4 hours, that's a good time right there, to make an orbit. Okay, an orbit is what theta? Well, one orbit is like one revolution around the Earth, which would be how many radians? Well, 2 pi, it's a complete circle. So the angular speed is going to be your 2 pi radians, that's your orbit, divided by 4 hours, okay, which is your time. 2 pi over 4 reduces down to pi over 2. So you get pi over 2 radians per hour. Okay, that's your angular speed. So if I take that angular speed and multiply it by my radius, which is 5,000, I get my velocity, or my linear speed. I keep saying velocity because it's a v. That's okay, same idea. The r is 5,000. The omega is pi over 2. Of course, I could reduce this. 5,000 over 2 is 2,500. So it's really 2,500 times pi. And of course, if I want to get a better approximation or a better feel for what that number is, I can punch that in to my calculator. And I get about 7,854. So that's approximately 7,854 miles per hour, okay? Because this is in miles, this was in, had hours in part of its unit. So we're going to be in miles per hour at this point. All right, now I may have rounded to, this may be an inaccurate rounding. It may be closer to 8,000 miles per hour because notice all of my other measurements are rounded off really to one significant figure there. You know, they're rounded to the nearest thousand. So it may be more accurate to call this 8,000 because if I go any more accurate, then I'm losing or if I use any more digits, I'm going to be losing some accuracy. So, but for now, this is good enough. Just be careful when you're using my math lab. Some of these applications are going to ask you to round to a specific place. So just be careful of that, okay?